my last video of the night. It's low-key late and like I'm tired. But no worries, because we're gonna do something pretty cool. We are going to like see the connection a bit clearer between the Fourier transform and the discrete Fourier transform. So how we're gonna start off today is we're gonna write the expression for the Fourier transform. So we say this guy is the integral from negative infinity to infinity of x of t e to the minus j 2 pi f t dt. Wonderful. I'm going to say that this can be approximated. Okay, no, I'm gonna say that from here. I'm going to argue that this can be approximated with the following expression. The sum from n equals minus infinity to n equals infinity. Okay. What I'm going to do is I'm going to discretize everything in this first expression. So remember, this goes all the way back to our discrete signals, the fun time we had with discrete signals. We should remember this expression, right? That relates my discrete time index n to my actual time t, where ts, sorry, this should be like a little bit clear, but t sub s is my sampling period. It's how much time is in between each sample. This formula should make intuitive sense. Let's plug that in here. We get x of, replace t with nts, and then replace t up here with nts. Now because here we're doing an integral and we have dt's, these dt's are little like kind of widths of the rectangles that we're integrating over, right? Here we're lacking that width. This is like the height of the rectangles, but we need a width to use. So because we can't use t anymore, we'll put ts here. Okay, so this basically, this ts plus the sum is the equivalent of the integral and dt, and then all the stuff inside here we just transform by turning t into nts. Okay, so I'm saying that I could, if I wanted to approximate this integral, I could approximate it with a Riemann sum in this format. So this is like a Riemann sum. If in calculus you probably learned that you take the limit of this Riemann sum, you take the limit of this guy, and then you get this guy, the integral. That's how you define the integral. Actually, that's a formal definition of the integral. Okay, great. Okay, so let's first now take this guy. So we take our x of f, and let's first cut it. So I'm going to make a remark here that I'm going to cut to n samples as we usually do. Okay, so instead of going over all of this stuff, because in the DFT we never really do that, I'm going to cut my summation to a finite number of samples. So now I have x of f is approximately ts times the sum from n equals 0 to n minus 1. Okay, that's looking nice. We're used to seeing that. Of x of nts e to the minus j 2 pi f nts. Okay, now here I would like you to recall one nice connection, which says that f, my continuous time frequency, is equal to my discrete time frequency over n times my sampling frequency. Okay, that's a formula we learned way back in Unit 1 when we talked about discrete signals, but okay, great. Rewriting this, write fs as 1 over ts, so this gives me fk over n ts, and all I'm going to do is I'm going to take that f and I'm going to plug it in here. So now I'm going to get x of f can be approximated by ts times the sum from n equals 0 to n minus 1, x of nts, okay, e to the minus j 2 pi f I'm going to replace with k over nts, over big NTS, and then what will happen? I'll be left with kn over n. This is incredible. This is great. This is wonderful. This makes me so happy. Convince yourself of the algebra if you need to. But if you look at what this thing is, well, this is just a discrete Fourier transform. We have some weird scaling here where, like, instead of just doing x of n, we're doing x of nts, but then we're multiplying by ts here. No big deal. This right here is a DFT. So pretty much what we're saying is that if we sample fast enough, if we get ts so small that these ts's start to turn into like dt's here, then we can approximate the Fourier transform with a discrete Fourier transform. Okay. In other words, that's a pretty cool idea. In other words, in terms of block diagrams, which we love as engineers, I could take a signal in time, and I have two options with it. I could first pass it through a Fourier transform, get out the Fourier transform version of it. Then I could sample that, okay? And what would I get out? I would get out the DFT. So I would get the DFT of my original signal. Sorry, this original signal, yes, the DFT of x of n, which is like the discrete version of my original signal in time. So my original signal in time is continuous. I could get out the DFT of its discrete version by doing this. I could also take another route, which is that first I could sample, then I could take the DFT, because once I sample, what do I get? I turn x of t into x of n. I turn my continuous signal by sampling it. My pink now makes a discrete signal, right? So very nice. So now I get a discrete signal. I can pass this discrete signal through a DFT, and boom. That's another way of getting out the same output, the DFT of x of n. In other words, big X of k. Okay, so all this is just saying is that we can approximate the Fourier transform with a DFT, and there's this nice like sampling transform, pair that we can apply to any continuous time signal as well to get out the DFT of the discrete version of that continuous time signal. Okay, great. Thanks for watching. We'll see you in the next video.